Hi, good morning. My name is Ibrahim Sallam. I'm a DPhil student here from the Department of Engineering Science. I come more from a machine learning and computer science background. In the next 10 minutes or so, I'll present to you our latest work in photo-Z estimation and some ideas for future work, especially when it comes to handling the uncertainties in input and output measurements. So I'm sure you all came across plots like these. This one is from Sanchez et al. You can see the results of many photo-Z estimation codes, template fittings, and machine learning models. And it looks like we've reached the limit, at least when it comes to the accuracy. Not because we can't come up with more sophisticated machine learning models to fit the data, it's just because the data is intrinsically noisy. The best model you can hope for will still have some scatter. And that's because the data looks more something like this, where given an input x, the best you can hope for is to provide an expected value because the relationship is not one-to-one. For any single input, you might observe many different output. And not only that, the noise or the variance is also a function of the input. You can see from this synthetic example in this plot where and the noise varies from region to region. So the next step is to provide an estimate of the variance as well. So and that variance prediction should be also a function of the input itself. So here's what most machine learning models do. They assume that the probability of observing y given x is distributed normal with some function mu of x and a constant variance sigma squared, where mu of x is some function of x. Could be decision trees, it could be artificial neural networks, Gaussian processes, you name it. But here's the main issue, that they almost all assume that the variance is constant, global, universal, regardless of x. In our work, we assume that mu of x is a linear combination of basis functions. So it's a basis function model, and these bases are squared exponential with parameters length scale lambda and center ci. Now we have to worry about optimizing with respect to these free variables, but we won't talk about optimization today. Let's just assume we have access to the best optimization code that will give us the optimal set of parameters. Even if you do that, the best you can hope for is to achieve something like this. Because obviously we assume that the noise is constant. This is the best you can do. The mean function is fairly smooth. It didn't overfit. This is what we hope and to find. But still, algorithms like Gaussian processes can at least give you some variable variance prediction in the case of data density variability. Like in this case, if you remove some data, it will increase the uncertainty because you haven't observed data here. So the variance will decrease in the areas where you observe more data and increase in areas you haven't observed data. You can also sample from the function, which is always good. But in order to fix this, we need to also assume that the variance is a function of the input as well. And we also assume that the function sigma is a linear combination of basis functions. Now we have these extra parameters to worry about and optimize with respect with. But again, don't worry about optimization here. Let's just assume we can just find the optimal set of parameters given any model. So now if you do this, you get something like this. Now, where the variance is also a function of the input itself. Not only that, notice that when I sample from the function here, where I haven't seen any data, the function itself varies a lot. Here, for instance, even though the data is noisy, the function doesn't vary as much because there's enough data to be sure about the mean function. So I can decompose the uncertainty into two components. One that tells me how certain I am due to the lack of data, and one that tells me how much of the noise is caused by intrinsic uncertainty about the imprecise measurements or imprecise features. So if you apply this to Phonazy, so apply this to the Buzzer Data Challenge release for this event. This is what you get, not just a scatter plot, but a color scatter plot, where the colors here indicate how certain you are about about your prediction. Note that the pattern, as you would expect, you're more confident along the x equal y equal x axis, and as you deviate from that, it becomes the uncertainty increases. And just to compare, I've run TPZ with 100 trees. It does provide some uncertainty estimate, but obviously it's not as good. And here's N and Z with 100 neurons, even worse. And to quantify this, you can basically choose a metric and compute that metric for different percentage of the data. So in this plot here, you see the RMSE score as a function of the percentage of data selected by the variance produced by each model. So for instance, let's say this point here is the RMSE for 40% of the data selected by GPZ after sorting the training set based on the variance prediction produced by GPZ, and likewise for TPZ and NZ. And as you expect, the more you add unreliable samples, the RMSE will increase. Okay, so that's when it comes to uncertainty about the output. Here's the paper, and we have the code available in Python and MATLAB. Please download it, try it out. Let me know if there are any issues. I'll be more than glad to help. But let's move on now to some ideas for future work. So now we have a model that, given x, we can provide a mean estimate and a variance estimate. But what if you're not even certain about your input? So you're giving in some input x, and you're telling me, hey, I believe it's plus or minus. Okay. So how do we deal with that? Now here comes the second advantage of using basis function models, especially squared exponential kernels, because we can exploit the fact that they look similar to or basically they're unnormalized Gaussians. Which can take that, use that to our advantage in a second. So far we've been assuming implicitly that x is distributed normal with mean of x and variance of 0. That, in other words, we're absolutely certain about the measurement. But if you're somewhat uncertain, most algorithm will just plug the expected value of the input if you're unsure about it, which in this case is just basically plugging x and ignoring the variance about the input. So you're using some useful information. So what we did is to compute the expected value of the response. Now the equations will change, and that variance in the input will serve us in a minute. So to do that, we know the formula for the expectation is basically you integrate with respect to x the function of x times the probability of observing x. And since phi of j here is basically a normalized Gaussian, we normalize it, take the constant out, it becomes here a convolution of two normal distributions, which we know the integration is which we know how to integrate, and after simplification you get this formula on the right hand side right here. Note that if sigma x squared is 0, this term will become 1, and this will go back to being just a normal squared exponential kernel. So this formula here is just basically a generalization of the squared exponential kernel, where you can add additional uncertainty about the input, and as that increases, this whole value is always obviously less than 1, so it will go to 0. This will also decrease the value on this term here. So the higher the uncertainty about the input, the closer this term will go to 0. In other words, you'll fall back to your prior. So I have a demo here to demonstrate on a univariate example. These are two plots. The one on the left is using the analytical method I've just explained, and the right plot is showing what we'd get if you use just sampling. You just sample with the mean of x and variance of sigma squared, and just average. So, whoops, let me just play it for a little here. So you can see they almost perfectly match. And not only that, the mean and variance changes as you increase the uncertainty about the input. I forgot to mention that the horizontal line shows the uncertainty about the input as it changes, and the vertical obviously is the uncertainty about the output. Okay, this is very critical for 40Z because in 40Z we are giving measurements and some error, associated error with each of them. So we can treat those as they like to be treated, as variances, not measurements or inputs. Because so far most 40Z codes use these as just part of the input. If we use that as variance on the input, we decrease the dimensionality of the input by half, which greatly improves the convergence rate and the accuracy you can achieve, and the number of basis functions you need, and the size of the training set you need. Because as you increase the number of dimensions on the data set, the space exponentially expands and it becomes sparser, everything becomes harder. Not only that, if in case of a missing data point, we can basically treat it as an input with infinite variance. That makes the math a bit easier, but not the optimal way to go. This is still work in progress. We're still thinking how to deal with this in a more efficient way. Like going back to photo Z now, this is a plot just doing the what people regularly do, just use the variance as input, and this is the output of GPZ, our code. And here's the result if you use the formula I just showed like 3 slides ago. Much better. The plot as you would expect it to look like as you deviate from the y equal x axis. The uncertainty increases, and it's much smoother and cool looking plot. So this is where we're at that now, right now, and thank you very much for your attention and listening, and I'll be happy to answer any question.